Hello, everyone, and thanks for joining me here. We're continuing the discussion on normal distribution, and in this video, we want to talk about a very important theorem. It's called central limit theorem, but in a very tangible and real-world way. One of the reasons that normal distribution is very popular and it's called normal because whenever a random experiment is replicated, the random variable that equals the average or total result over the replications tend to have a normal distribution as the number of replicates become larger. So let me give you an example so we would better understand that. So let's say the experiment is throwing a die 100 times, right? And your random variable that you're recording is total number of times a die lands on 6, right? We all know that on a single throwing a die, that probability is 1 over 6. So if you were to calculate the expected value of x, which is going to be expected value of total number of times you get a 6, it's going to be 100 times 1 over 6. So on average, you're expecting to see 16 or 17 times that die lands on 6 in that experiment. If you were to repeat this experiment for many times, how would the distribution of x look like? So if you were to repeat this experiment, you would throw a die 100 times, and then you record x, and then you would throw the die 100 more times, and you record x. How would the distribution of x look like? Well, actually, I simulated that in computer, and here we're looking at 400 replications of that experiment, and every time I recorded x. The first experiment I got 16 sixes, and then 17, 18, 15, 15, 14, all the way. And I calculated the average of that column, that is 16.65, which is very close to the theoretical average of this random variable. But the more important observation is that if you were to graph the histogram of this random variable, you would see that it looks or it behaves like a normal random variable, right? Most of the time, you'll get 16 or 17 sixes, and as you move away from those values, the probability of getting 20 sixes or 13 sixes is a lot less. The random variable that equals the average or total result over replications tend to have a normal distribution. And here x was the total number of times we get a 6, and that behaves in a normal fashion. So that's why normal distribution is very important. I want to give you another example. Steph Curry, a famous basketball player, his performance on three-point shoots is 44% success on average. Assume that he gets to shoot 10 times in each game. So the experiment is shooting 10 times. The random variable is, again, total number of times he makes it. The average of that random variable is 4.4 times. So on each game, you're expecting to see 4 or 5 times success for the most part. But there are some games that he probably, going to make it 7 times or 8 times out of 10. But if he plays 100 games in a season, how would his performance per game look like? Well, again, you would clearly see that a normal distribution would be a good approximation here. I replicated that experiment, right? Every game 10 times and 100 games. You can see that for the most games, he would have 4 or 5 times success, and as you move away from the average, the probability goes down, but it behaves like a normal distribution. So that's why normal distribution is very important in practice because we can model the behavior of systems oftentimes using normal distribution.